All right, thanks, Renee. Are you able to see my screen?
Yes, we are.
Great. All right, well, hi, everyone. So this talk is going to be a quick run through on how we can automatically extract faults from models of continental extension. This is some work that John and I have been doing. But first, to give a little bit of background. So my PhD is mainly focused on how normal faults grow during rifting. And this has mainly been done using observational data, so measuring faults in the subsurface. So I thought I'd show you a quick example of what this looks like for all you modelers out there. This is off the northwest shelf of Australia. The length is approximately 40 kilometers. And what we've done is we've mapped this seismic volume to reveal the fault geometry. So what we would do then is we would measure a fault, would measure usually a key property would be the fault length. And also its maximum displacement. And if we plot these two properties, we'd get this relationship that looks fairly like a linearly scaling relationship. And from this, we would determine how faults might evolve with respect to their length and their displacement. The problem with this is that it's quite a crude geometric observation, and there's not that much time constraint here. In fact, I think the only data set is this one. So the lack of kinematic and dynamic understanding is like not really there right now. So models could really help with this. And so this was our main motivation. It was to do a big statistical comparison between faults produced from the models and that are observed in order to gain some temporal understanding for fault growth, but also to see whether the inferred physics from the models actually produce anything like what we see in the subsurface. So our model setup is quite similar in design to John Naliboff et al. 2020 paper. But one of the main differences is how we prescribe an initial plastic strain in the crust. So usually you might use something like a weak seed or a randomized distribution. So that would look something like this. Here, what we have are these little blocks. Each block is 5 kilometers, and they're prescribed a random value between 0.5 and 1.5. And what we've done in the model is we've looked at each of these different blocks, and if the initial strain is above the value of 1, then it's rounded up to the maximum value, which is 1.5. If the value is less than 1, then we assign that the minimum strain value, so that's 0.5. And what you're left with is these sort of strong and weak blocks of 0.5 and 1.5 that have this sort of spatial significance to them. And what's quite cool is that if you vary the block size, so the blocks were 5 kilometers, but now they've reduced down to 2.5 kilometers, you end up with a different distribution of these strong and weak blocks. So this is something that we have investigated along with a few other parameters, but in this talk, I'll just be showing you one of the models. The model will be using the 2.5 block initial plastic strain. So that would look something like this, but it wouldn't look exactly like this because every time you run the script, it will generate a new randomized statistical distribution. So yep, here on the left, we have the strain rate showing active deformation. And on the right, we have the non-initial finite strain, which is just the finite deformation, but removing the initial strong and weak blocks. So the models are going to run for 5 billion years. And just by eye, I mean, I think that the fault patterns look quite realistic, so that's encouraging. What's also nice is you get these discrete fault structures from which we would extract certain fault properties. So when it comes to fault extraction, initially, John and I found it quite tricky to find a solution for this. That's because conventionally, image processing techniques would use a binary threshold. So that's using a manually determined cutoff point. And so anything that's less than this cutoff point would be assigned 0, and everything above this would be assigned 1. Then the connected regions would be labeled as independent faults. So here the different colors are different labels, and this is using scikit-image, which is a Python package. And what we found is if you use a generous threshold, there's just too much connectivity. So say here, this is all labeled as one fault. So if you're looking to extract properties such as the length, then you can't really do that here. On the other hand, if you use a high cutoff point, we do get these individual fault labels, but it's only really picking up the highest points of strain, and you're really missing out on a lot of the interaction from the rest of the fault network. So what we did is we used the same Python packages as the previous example. So that's mainly scikit-image. We also use quite a lot of NumPy, and if you're planning on plotting, then we use pandas as well. What we used as an input image, well, you can use whatever you want. So you can use the non-initial finite strain, you could use the strain rate. We opted to use the vertical depth derivative of velocity. So that looks something like this. And the reason why is because this reveals the dip direction of the faults. So that's another property that we could add to compare with other things later. So our method revolves around taking the derivative of the input image. We then normalize the values so that they're between 0 and 1. And what you can see here is a value of 0 on one side of the fault, and then a value of 1 on the other side of the fault. So if we want to then extract the difference of this again, we could then reveal the locations of those faults. So then taking a binary threshold of that and applying the labeling to the faults, when we compare that with a sort of input of the strain rate, we're much happier with this result because it allows you to retain the complexity of the overall fault network, but you don't have to manually define a fault threshold every time, especially if you're looping through different time steps. And also the faults are labeled as discrete segments. So that allows us to extract properties such as the length, which I have here. And also I've plotted the orientation, so the strike direction of the faults as well. So yeah, if we run this script throughout the 5 billion years, this allows us to plot some key properties against the observational data that I showed you earlier. So this is starting from the first time step and going through time, it looks like this. So in general, what we're seeing is that there's this sort of upwards trajectory, which means that the fault lengths were established really early, basically from the first resolvable increment, and then it sort of gained strain or displacement through time. However, when we plot the individual properties, so this bottom figure here, you can see this red line, and this shows the maximum length of an active fault in a given population through time. This is just to show that there's actually a lot of variation through time of the active fault length. So when we have a further look, this is plotting the strain rate against length of a fault through time. Yeah, this is just to show that even though the length might have been established quite early, there's actually a lot of transient deformation, a lot of strain rate variation through time. And this typically gets characterized into two sort of end member distributions. So either the faults would be localized in a given time step along its entire length, or in another time step, the distribution might be well, a lot more distributed throughout the crust. And our fault extraction seems to be able to extract that quite well as well. So yeah, to conclude, there's a big lack of temporally constrained data sets in observational data. Numerical models are now able to document this fault evolution to a pretty good resolution. And our image processing extraction script allows us to automatically extract the properties without the need of defining some sort of threshold. And this has showed us that there are some pretty uncanny similarities between the faults from the models and observational faults. But this extraction has actually revealed even more. So revealing that transient deformation in the model data. So yeah, this code will be released in an upcoming publication, and we're planning on making this into an open repository with additional features. But if you're interested in any of this, then feel free to chat to me or to John. We'll be happy to talk. And that's it. Thank you.
Awesome. Thank you.